let's look at radioactive decay as part of the A-level specification. It will trigger me for the fact that I haven't completed the brackets up there. Let's say we have got 100 dice, and let's say that we were to roll them out into a draw, and every time it landed with a 6 at the top, we would remove the dice from the draw. Now, the probability of ending up with a 6 on the top is a 6, okay? Assuming that it's not a loaded die. So, if we rolled 100 dice, we would anticipate that we would be removing a significant value and that we wouldn't have 67 left, would we? Because 100 divided by 6 that would mean that we've lost 33. So let's get my calculator. We would actually have, and I'm going to cross this out, 100 divided by 6, which means that we lose 16.6 and take that away. So we would have 83 left. 83.3 approximately, if we use an integer values with that. So in terms of the 83 that we've got left, if we roll again and we roll again until we've got none left, then our graph would follow this exponential decay curve because there would be less dice left as we go through. The probability of them decaying remains the same because there's less dice. The activity, so the amount I'm removing each time, decreases. Now, radioactivity works in the same way. If we have got a box of unstable nuclei, then there is a probability that the nuclei will decay. So, for example, the decay constant for uranium-236 is 1.546 times 10 to the minus 10 years. Okay, so that means every year 1.546 times 10 to the minus 10 of the nuclei will have decayed. If we have a look at polonium-212, as another example, look how fast that's decaying. So 2.28 times 10 to the 6 are decaying every second. So this would have a really short half-life, it would have it at the order of nanoseconds. This would have a really long half-life, because this would not take long to decay at all. So, the amount of decays that are occurring per second, which is measured in becquerel, is equal to the decay constant times by the number of unstable nuclei that are present. Okay, so the amount that are decaying per second depends on how many nuclei you've got, thinking about the dice, and what the probability of decay is. And that is the decay constant here. And every radioisotope will have a different decay constant. So the decay constant is per second. So, activity is the number of nuclei that have decayed in a set time period. Okay? The negative is there because it is a decrease in nuclei. Okay? Now, if we put that equal to that, because they are both equal to A, then we end up with the change in nuclei divided by the time that's elapsed is equal to the negative decay constant multiplied by how many nuclei there are present. Now you could rearrange this to put change in nuclei at the top and amount of nuclei present at the bottom, and that shows an exponential decay pattern when you've got a rate of change of its own quantity occurring. Because it's a radioactive decay pattern, then we have got number of nuclei present is equal to the number of nuclei that it had at the start, which is represented by n with a 0 at the bottom. And then you've got E, and then you've got the negative decay constant times by time. If we recall from earlier that the natural logarithm of an exponential is equal to 1, so if you need to rearrange it to get the decay constant and time, then rearrange it so you've got n over n naught is equal to exponential negative decay constant times by time. And then what you do is you take natural logarithms to turn the E into a 1, so that disappears from the equation. If we were to plot this as a graph differently to the one that we had earlier, what we would have is we'd have the natural logarithm of the number of nuclei on the y-axis, we'd have time on the x-axis. The y-intercept would be the initial initial number of nuclei, and the gradient would be the time. The decay constant. So you'd be able to find the decay constant of the material that way. Things that you need to do with this is practice. This is perfect for highlighting the values that you've got, going to the data sheet and selecting the appropriate equation. Just as a reminder, you can't get away from moles and Avogadro's constant with this. They may use the word nuclei and atoms interchangeably. So, 1 mole of hydrogen is equal to 1 gram. That means that there are 6.02 times 10 to the 23 atoms present in that mole. 1 mole of oxygen, okay, it's an atomic particle, it's 32 grams, and you've got Avogadro's constant number of atoms present in that as well. Okay, so if you've got a certain number of moles given, the number of atoms present is the number of moles times by Avogadro's constant. Don't be put off if you see the equation in that form where the n's have been replaced with a's. Okay, the activity exponential equation works in the same way, and that is because activity is proportional to the number of nuclei present. Take your time with this, do plenty of practice. I would highlight the values and I'd highlight the constants in the question. Remember, we are dealing in seconds, so if it's in years, you need to figure out how many seconds there are in a year. Thank you.